Eolic energy. Eolic power. Wind power is the conversion of wind energy into a useful form of energy, such as using wind turbines to make electrical power, windmills for mechanical power, wind pumps for water pumping or drainage, or sails to propel ships. Dutch wind farms consist of hundreds of individual wind turbines which are connected to the electric power transmission network. Wind power as an alternative to fossil fuels is plentiful, renewable, widely distributed, clean, produces no greenhouse gas emissions during operation, and uses little land. History. Mechanical power. Sailboats and sailing ships have been using wind power for thousands of years, and architects have used wind-driven natural ventilation in buildings since similarly ancient times. The first windmills were in use in Persia at least by 9th century and possibly as early as the 7th century. Windmills were used extensively in northwestern Europe to grain flour from the 18th to 1881. Lord Kelvin proposed using wind power when coal ran out, as so little of it is left. Solar power was also proposed at about the same time. Electrical power. In July 1887, a Scottish academic, Professor James Blight, built a cloud-sail wind turbine in the garden of his holiday cottage in Mary Kirk, and used the electricity produced to charge accumulators which he used to power the lights in his cottage. In 1975, the United States Department of Energy funded a project to develop utility-scale wind turbines. The NASA Wind Turbines Project built 13 experimental turbines which paved the way for much for the technology used today. Since then, turbines have increased greatly in size, with the Econocon E126 capable of delivering up to 7.5 megawatts. Wind turbine production has expanded to many countries, and wind power is expected to grow worldwide in the 21st century. Wind energy. Distribution of wind speed. The strength of wind varies, and an average value for a given location does not alone indicate the amount of energy a wind turbine could produce there. To assess the frequency of wind speeds at a particular location, a probability distribution function is often fed to the observed data. Different locations will have different wind speed distribution. The waveful model closely mirrors the actual distribution of early 10-minute wind speeds at many locations. The Weibull factor is often close to a second, and therefore a Rayleigh distribution can be used as a less accurate but simple model. High altitude winds. Power generation from winds usually comes from winds very close to the surface of the Earth. Winds at higher altitudes are stronger and more consistent and may have a global capacity of 380 terawatts. Recent years have seen significant advances in technologies meant to generate electricity from high-altitude winds. Wind power capacity and production. Growth trends. In 2010, more than half of all new wind power was added outside of the traditional markets in Europe and North America. This was largely from new construction in China, which accounted for nearly half the new wind installations. The forecast to 2013, the expected average annual growth rate is 15.7%. More than 200 gigawatts of new wind power capacity could come online before the end of 2013. Wind power market penetration is expected to reach 3.35% by 2013 and 8% by 2018. Capacity factor. Since wind speed is not constant, a wind farm's annual energy production is never as much as the sum of the generation nameplate ratings multiplied by the total hours in a year. The ratio of actual productivity in a year to this theoretical maximum is called the capacity factor. Typical capacity factors are between 15 and 50%. Values at the upper end of the range are achieved in favorable sites and are due to wind turbine design improvements. Penetration. Wind energy penetration refers to the fraction of energy produced by wind compared with the total available generation capacity. There is no generally accepted maximum level of wind penetration. The limit for a particular grid will depend on the existing generating plant's precise mechanism, capacity for energy storage, demand management, and other factors. Variability. Electricity generated from wind power can be highly variable at several different timescales, hourly, daily, or seasonally. Annually variation also exists, but it's not as significant. Wind power is, however, variable, but during low wind periods it can be replaced by other power sources. Transmission networks presently cope with outage of other generation plants and daily change in electrical demand, but the variability of intermittent power sources such as wind power are unlike those of conventional power generation plants, which, when scheduled to be operating, may be able to deliver their nameplate capacity around 95% of the time. Predictability. Wind power forecasting methods are used, but predictability of any particular wind farm is low for short-term operation. For any particular generator, there is 80% chance that wind output will change less than 10% in an hour and a 40% chance that it will change 10% or more in 5 hours. Reliability. Wind power hardly ever suffers major technical failures, since failures of individual wind turbines have already any effect on overall power, so that the distributed wind power is highly reliable and predictable, whereas conventional generators, while far less variable, can suffer major unpredictable outages. Integration with other sources. The combination of diversifying variable renewables by type and location, forecasting their variation, and integrating them with dispatchable renewables, flexible fuel generators, and demand response can create a power system that has the potential to meet power supplies need reliability. Integrating ever higher levels of renewable is being successfully demonstrated in the real world.